recovery of gravity waves from bottom pressure.
Thank you, Olga. I would like to thank the organizers for inviting me. Sorry, running too fast. And congratulations, Jean-Marc, for your 60-10 birthday. I'm going to talk about recovery of free surface from bottom pressure measurements. But before I start, let me acknowledge my collaborators, Joris Labarbe, who is a postdoc with me in Nice, and David Henry from University College in Cork. So what's the motivation for this work? Is to measure the shape of the free surface from at sea. In the lab, we have a lot of equipment to measure the waves, but in a real environment, it's more complicated. So ideally, we want something that is not intrusive, that is not perturbating the wave, something that is easy to maintain, that is safe from boat. Or if you imagine a floating buoy, for example, you don't want a boat to impact the buoy. And of course, it has to be cheap. And one solution is to put pressure gauges at the bottom of the sea. This has been done for decades. And it's cheap in terms of making the equipment, but it's also cheap in the sense that it's hardly stolen, because this is a main issue in the real life, is equipment gets stolen. So, and I'm very serious. So it's one of the motivation for using this kind of equipment. Then the question is, how do we recover the free surface from the bottom pressure? So how we do that? So as I said, it has been done for a long time. And typically in a simple situation, the problem is like that. Let's consider a two-dimensional problem, a flat horizontal bottom, a steady wave. So it's a wave traveling with a constant speed, with a permanent form shape, and we're travel with the same speed as with the wave. So for us, the flow is steady. There is no time in this problem. So we know the pressure at the bottom here, and we know from Euler equation that the pressure satisfies Poisson equations. So we have to solve, and we know that the pressure at the free surface, if we neglect any surface tension or wind effect, the pressure is equal to the atmospheric pressure, that is a constant, and this constant we can take it equal to 0. So we know the pressure at the bottom, we know the pressure at the free surface, but we don't know the shape of the free surface here. And of course, we don't know the source term in the Poisson equation here, because the velocity field is unknown. So basically what we have to do is to solve an unknown equation in an unknown domain. Okay. So that's what is called inverse problem. So we don't know all this information, but we know the laws of physics. We know the equations. So we are going to exploit that to solve our problem. So let's be a bit more precise. Oopla. So I will consider in the simplest case, it's an academic problem. It's not an engineering problem for real life situation. So I consider a two-dimensional problem, a permanent flow, a perfect fluid, a constant vorticity that is unknown a priori, a flat horizontal bottom that is impermeable, but we don't know exactly where it is. We don't know the water depth. So D is the mean water depth that is unknown. The acceleration to the gravity that we assume we know it. P is the small p is the relative pressure, is the pressure divided by the density. Since the density is constant, I want to get rid of it. X and Y are the Cartesian coordinates that are known. U and V are the corresponding velocity component that are unknown. Psi is the stream function that is unknown. And eta is the profile of the free surface that is unknown. So if we, with this assumption, we can write the equation of the problem. These are well known, so I will not go into too much details, but the stream function satisfies a Poisson-like equation where the right-hand side is minus the vorticity, that is a constant. We have the impermeability of the bottom that says that particle at the bottom remains at the bottom. At the free surface, we have the same kind of condition. The fluid particle at the free surface remain at the free surface. And at the free surface, the pressure is constant, and this constant is taken to be equal to 0. So the Bernoulli equation at the free surface, that is a first integral of the Euler equation, is written like that, where Bs is a Bernoulli integral at the free surface. Substrictly.
You don't have the vorticity in that last equation.
Yes, it's in there.
I think BS, yeah. Okay.
Because when you integrate Euler equation for potential flow, the Bernoulli constant is a constant, but for vorticity, B is a function of the stream function. And the derivative of B is plus or minus half the vorticity or something. It's an antiderivative of the vorticity. Okay. So that's the kind of problem we want to solve. But I will start to explain the philosophy for potential flows first before moving to rotational case. So a bit of history here. For a long time, people have been using, or they are still using, probes assuming hydrostatic pressure to recover the free surface. So hydrostatic pressure means that it's just the weight of the water above the probe. Yeah. And then from P, you can find eta. This is very simple, very easy to implement. The point is that this assumption neglects the fact that the fluid is moving. Okay, so there is no motion. So in case of tsunami or storm, you don't need the Nobel Prize in physics to argue this assumption. Okay. And some studies have shown that even for moderate wave, you can make some large errors. So the next type of model is a bit better, is to consider linear wave. So you have a linear wave traveling at the free surface, which is a sinusoidal profile, and you use the linear theory to determine your free surface from the bottom pressure. But this assumption too can lead to large errors, especially for large wave. So there have been more sophisticated technique, and it's possible to reformulate the equation, the system of equation, into a single equation for the free surface, like Katie here did. So they obtain an equation here where you have a derivative here squared on the denominator of a fraction with a square root, and on the right-hand side here, you have a Fourier series with Fourier coefficient defined by the bottom pressure, but here you have also your unknown. So this is a highly nonlinear, I don't know how you call that, integral differential equation. So it's a bit complicated. And you can solve that numerically. I mean, they did solve it numerically. But for practical application, we would like some equations that are easier to solve. And actually, it turns out that this equation can be solved analytically. So how is it working? First, we consider a new quantity that we call the complex pressure, Gothic P here. I will come back in a minute to explain what it is and where it comes from. And you can derive a differential equation on this form that is simpler than the previous one. And that can be solved numerically as well, and we can prove convergence, unicity, or whatever. But actually, this equation can be solved directly, analytically, in this form, where Q is an antiderivative of P. And here you have, if you look at the right-hand side, yeah, you have a quasi-quadratic equation for eta. So a quadratic equation, you can solve it, okay? And then you have eta as a function of eta, because eta is also hidden inside the definition of QS. But this function Q is a pure function. It's no integral, no derivative into that. So actually, this is an algebraic expression. When we deal with differential equation or integral equation, what we call a solution is an expression that does not involve integrals or derivatives. So this is an exact analytical solution in an implicit form. So when you solve that for eta, you can just apply a fixed point iteration and you can prove that it's converging, and it's even converging for the limiting wave, the Stokes wave. It's semi-converging from below. So that's quite a robust approach, and it's very easy to implement. You just implement your most stupid fixed point iteration and it does converge. So now let's look at the case of the constant vorticity. So constant vorticity from a calculus viewpoint is pretty much the same as potential flow, because actually we can get rid of the current. So In the literature, there are much less reference than the case of potential flow. There is a linear approximation by Henry and Thomas, and weakly nonlinear up to the third order, I guess, by Vera, where they reduce the problem with some small amplitude assumption, and they end up with, you have to solve a differential equation at the end to recover the pressure. It's not completely direct. But what I want to show you is that even in that case, the problem can be solved analytically. So how do we do? Since I have this linear shear current, I make sort of Helmholtz decomposition. I subtract from the velocity field, from the I subtract here the current, and I define the capital velocity here, the potential part of the flow. And this velocity satisfies the Cauchy-Riemann relation. So then I can use complex variable, because I'm a maniac. I want to use complex number all the time. My students do not think it's a good idea. So when you do that, at the bottom, the capital U equal the small one, the vertical velocity is 0, h is the total wave height. So you have this relation. And then since U and V satisfies the Cauchy-Riemann relation, I can introduce the complex velocity here. So that's my starting point. Okay, now if I look at the Bernoulli equation at the free surface, yes, okay, we have this expression, it's just basic formula, but it's more interesting is at the bottom here. You can solve it for U, this expression. The minus sign here doesn't matter, it depends where you want. If you're in a fixed frame of reference, if you want your wave to go to the right or to the left. So you have U at the bottom as this expression, which depends on the bottom pressure. But we know that since V is 0 at the bottom, if we make an analytic continuation of U, we have the complex velocity. The complex velocity is just U bottom, where you replace X by Z. And for me, complex analysis is just get rid of X, call it Z. So, and with this expression here, we see that this quantity appears. That is an analytical continuation of the bottom pressure. I have to say, the pressure itself is not the real part, or nor the imaginary part of an holomorphic function, because it's not an harmonic function. So when I make an analytical continuation of the bottom pressure, I do not get the physical pressure. These two functions match only at the bottom. The physical pressure is 0 at the crest, but the complex pressure is, let's see. So I introduced this Gothic pressure, or complex pressure P here, where I modified a bit the original version to account vorticity parameter. And you can see that at the bottom, the complex pressure reduced to the bottom pressure. It has been constructed for that purpose. And I also introduce an antiderivative of this function, okay? Where I choose the origin where I want, but I want to choose it at the crest of the wave at the free surface, so I can integrate along the free surface. And that's it. Now, if I want to know what this Gothic pressure is at the surface, I just have to look at this definition here to write it at the free surface, and with the Bernoulli equation and the impermeability of the free surface, I get an expression for P and then for Q. And then after 2-3 lines of calculus, it's straightforward. You get this equation for the Q function, which is no longer quasi-quadratic, but quasi-cubic. Okay, and I have a modified Bernoulli constant here that is a combination of the bottom and free surface Bernoulli constant. If you differentiate that and you make some algebra, you have also this generalized differential equation. But I'm not going to solve the differential equation. I prefer to consider its solution. That would be simple. So it's quasi-cubic. So in practice, how does it work? Suppose you have bottom pressure data. You fit some function, you find it suitable for your signal. Here I consider Fourier series. It will not work for solitary wave. You can fit a cnoidal elliptic function, the function you like. So you have to choose a basis of function that is good. It means it's as accurate as possible with as few as possible terms. So you fit that by here, it's a least square minimization, what I do. It gives you a definition, the zero harmonic gives you the definition of the water depth, and then you get the harmonic here. And they are determined directly from the bottom pressure once for all. So now I want to compute my complex pressure. So I just replace X by Z plus YD. How difficult is that? I can do it. So I have my holomorphic pressure here. And if I want the complex Q function, I just integrate exponential. I can still do that. So this is and that's it. I just apply this Q function at the free surface and I have it. So, except that I have some unknown parameters that I have to. So first is the Bernoulli constant here, or the pseudo Bernoulli constant. So to find it, I apply my formula at the crest and at the trough. So it gives me a relation between for B hat as a function of the amplitude. A is the amplitude from rest to the crest and B from the rest to the trough. And A plus B is the total wave height. So I have this expression. But now I replace one unknown by two unknowns. So I have to find more relation. But when I obtained my equation for Q, it was an imaginary part of a complex expression. But you also have the real part, the conjugate. And that gives me the extra information I need. So I don't do it for Q, but for P because I find it more convenient. So if I apply P at the crest, we end up with an expression here where the Japanese bracket means average along a wavelength. Okay, so we have an expression for one at the crest, one at the trough. So we have two equations for two unknowns. Of course, this is implicit, but we have to solve the implicit problem anyway. So it's just a few more unknown into your system of it. But now, the last question is, I have one unknown left, the vorticity. How do I know the vorticity? If you look at one point, if you know the pressure, you cannot know the vorticity. They are somehow orthogonal quantities. This is true locally, but globally, when you have vorticity in your field, it changes the velocity field and the profile. So it changes the pressure. So if you know the problem globally, you are able to find the vorticity. And how do? We apply the same equation. We have used the crest, the trough. So let's take a point in between. First good idea would be to take half wave. The problem is that when you have a solitary wave, half infinity, it's still pretty far away. So we don't do halfway horizontally, but halfway vertically. Be quite some distance. So we look at an abscissa x naught, we don't know, that is halfway between the max and the mean. And then we have, at this point, we have the imaginary part and the complex pressure. We have three quantity that provides three relations for x naught, for eta, and its derivative and omega. So we close the problem. So how we solve it? We use fsolve in MATLAB. You use your Newton method, your Levenbank marker, whatever solver. And this is quite easy to implement. So let's see some examples. Here we consider quite a steep wave. So on the top, you have the bottom pressure here. We look at its Fourier spectrum, and we see that the Fourier coefficient decay exponentially, and here we have reached machine precision. So we get rid of this one because this is just junk noise. And from this Fourier polynomial, we rebuild the free surface here. So the red line is the recovered surface, and the blue circle is the original one. And you see that it's quite accurate. In that case, the length of the depth is 2 pi, about 6. It's quite deep. And the deeper the water, the more difficult the recovery. You have to understand that this problem is ill-posed. Any error at the bottom is increased exponentially. You move away from the bottom. Okay. Here it's an extreme case. We have about 4-digit accuracy, but if we consider more moderate, we can get 10, 11 digits. But the fact that we have only 4 digits, it's not because the method is bad, it's because here, when you cut here, you have some Fourier modes that are below machine precision, but when you amplify them exponentially, they contribute. But since you don't have them, you cannot create information that is not there. So this is inherent to them. So let's look at another example. Here it's a wave with stagnation point into the wave. So you have two stagnation point at the bottom, about halfway between crest and trough, and one stagnation point below the crest in the middle of the free. There are three stagnation points. So here is the profile on the top of the pressure, the Fourier coefficient here, we stop here, and this is the recovery. The free surface is close to a cosine function, but the field is not, it's far away from that. Huh? And since we are working in the physical plane, the fact that we have a stagnation point is not at all an issue. We don't care. When you use the stream function as an independent variable, then you have a problem when you have stagnation point. But here, you have stagnation point, so what? And I have to mention that also, the vorticity is also recovered by a 4-digit accuracy in these extreme cases, which is not too bad. So now the question, we know that for with vorticity, we can have overhanging wave. So we generalize this approach to recover overhanging wave as well. So we have the algorithm, but our difficulty is to find the wave first, because I don't use experimental data. I don't have that. So I have to solve the equation first to obtain the pressure at the bottom and to see, to compare, to make the recovery. And apparently we use the algorithm, one algorithm from Jean-Marc and one from Da Silva and Peregrine. We did pretty much the same thing. And we cannot get more than 8-digit accuracy. So I don't know if we do something silly with the numerics or if it's the limit by the formulation. When you have complicated expression, for example, if you want to solve an equation with a square root around 0, you lose half of the digit accuracy when you're working with floating points. But perhaps there are other tricks, so I don't know. So if you have some suggestion, we can in principle recover, but as I said, if we don't have enough harmonic, then the recovery is bad. So we have to obtain the solution in the first place. Okay, so in summary, we reformulated the problem. We did it mostly analytically. The numerics is quite easy then because it's algebraic and thanks to the function. So here are the references if you are interested. And since we are talking about the next 20 years, I have to put some perspective. It will be interesting to have some mathematical proof. For the potential flow, we have proven pretty much, we don't know everything, but quite safe. We know unicity, convergence. But in the case of vorticity, we don't have as many results. And it will be interesting to have more results that we can exploit to devise a better numerical algorithm for recovery. We can think about the generalization of this problem. Of course, you will not always end up with algebraic solution, but you may end up with a simpler equation to solve. So the case of non-constant vorticity, in case of linear vorticity, I think I can do it. For arbitrary vorticity, I don't know yet. We can consider surface pressure, wind, capillarity, whatever. That's doable. And steady motion, in case of potential flow, I think it's doable. Varying bottom, I haven't tried it yet. Perhaps it's feasible, and maybe three-dimensional case. And in a longer perspective for practical application, how do you do this ill-posed problem in case of noisy data, outliers, and even unstationary? This is a far ahead goal. So I guess I kept on time. Thank you very much.